back to my today's session on network analysis, and today I am going to tell about the Q factor and bandwidth. Myself Dr. Sayanti Chatterjee, Associate Professor of Electrical and Electronics Engineering Department. So as I discussed before starting, I will tell about the course objective. So the course objective of my today's class is the second one, that is the transient analysis and steady state analysis of the DC and AC circuits, and we will basically here we will discuss about the AC circuits only. And what is the outcome of my today's class? The main outcome of my today's class is to discuss the steady state response and response of electrical circuits to AC supply. So this is our main word today, resonance and AC supply. In my previous two lectures, I told in details about the resonance of AC supply. So today we will go a small recap, and then we will go for the Q factor or quality factor and bandwidth. So what is the AC through an RLC circuits? First we will discuss about an RLC series circuit, and RLC series circuit, as we know, the current is fixed throughout the AC RLC circuit. So the circuit shows the resistance, inductance and capacitance, or VR is equal to IR. VR is equal to IR. What is VL? VL is nothing but the I into XL. And we can also write that what is XL? XL is nothing but the 2 pi F into L, and VC is equal to I into XC, and XC is nothing but the 1 by 2 pi FC. So what is the total voltage? If we use the KVL here, we will get V is equal to VR plus VL plus VC. And remember one thing, that the voltage, as this is an AC supply, it has a magnitude as well as the phase difference. So the voltage addition cannot be a scalar addition. It must be a vector addition. Vector addition means VR plus VL plus VC, it will with its magnitude as well as phase angle. So we can also write VR is equal to I into R. If we are taking magnitude only, I into R into I into XL plus I into XC. And what is VP is nothing but the Z. So if we compare the RHS and LHS, we will get Z is equal to R plus J XL minus XC. Or we can write magnitude of Z is equal to R square plus XL minus XC square, and the angle phi is equal to tan inverse XL minus XC. We are writing by X, or we can write XL minus XC by R. So this is the basic, these are the basic equations of an AC RLC circuit. And also we have discussed about the phasor diagram. Just one quick recap, that phasor diagram is, say we are giving the current I here. So I is the constant, so we will take it as the base. So what is the voltage? Voltage will be voltage across VR. Voltage across VR will be in phase. So VR is in phase. What about the VL? Again, we will go for the civil rule. So in an inductor, the voltage is leading the current. So this is our VL and this is our VC. So what is the VL minus VC? We know that the inductor is always leading by 90 degree and the VC is always lagging by 90 degree. So VL and VC is always 90 degree apart. So what is VL minus VC? This is our VL minus VC. So what is the voltage? VR plus VL minus VC. So this is our voltage using the phasor addition, and this is our new angle phi, which is known as the phase angle. If we draw it for an inductor and capacitance for the passive elements, what is VR? VR is nothing but the IR. This is I into XL and this is I into XC. So if we are dividing everything by R, what we are getting R. This is our only R and this is our XC. So what is the XL minus XC? So this is our XL minus XC. Now it is not necessary it should be in the positive side. It may be in the positive side, it may be on the negative side depending on the value of XL and XC. If XL is greater than XC, then both will be in the positive side. If XL is less than XC, it should be in the negative side. So it is depends on totally the value of XL and XC, and we are getting the Z here. Now this is one case. What is the another case? Another case I will draw here. So what is the another case? Another case is if this is XL minus XC, this is the resistance, then the Z will be in the downward. So both can happen based on the value of XL minus XC. The important topic is what will happen when the value of XL is equal to XC. So what is happening when XL is equal to XC? So this is our again R, XL and XC. And we are taking XL is equal to XC. So they will cancel out each other. So both will be 0. So the R is equals to Z only. And this condition is known as the resonance condition. So what is the resonance condition if we draw? VL or VC or XL or XC will cancel out each other, and as a result the Z will be equals to R, and voltage and current will be in the same phase. As we know, the current through the resistor are always in the same phase. The resistor through the current through the resistor is always in the same phase. So we can write here XL is equal to XC. So XL is equal to XC means 2 pi FL is equal to 1 by 2 pi FC. F square 1 by 4 pi square LC. FR equals to F naught is equal to 1 by 2 pi root of LC. Or we can write what the unit is always hertz. What is omega R? Omega R is equal to root of LC and the unit is radian. In your problem, any value may come in the exam. So in this value, if 1 by root of LC, so we got the relation. First is the resonance frequency in radian. Resonance frequency in the FR means resonance frequency in hertz. Next we are getting that the Z is equal to R, and Z is equal to, because then what is about the current? The current is I is equal to V by R. Previously current in the resonant condition was V by Z. Now this is V by R. So the current will be maximum. Next we will move to the RLC parallel circuit. So first we will start with the basic RLC parallel circuit. What is this? R, L and C are in parallel and we are giving one voltage source. So when the parallel resonance will occur? Parallel resonance occurs when the supply frequency creates zero phase difference between the supply voltage and current, producing a resistive circuit. So what is the parallel circuit? Parallel resonance occurs when the supply frequency creates zero phase difference between the supply voltage and the current, producing a resistive circuit. The resonance occurs in a parallel circuit when the total circuit current will be in phase in voltage. Means the original current, there is no phase displacement between the voltage and the current. As to reactive component, this is one important term here. Two reactive components cancel each other out. Reactive components means inductance and capacitance. XL and XC both cancel each out. So the resonance and the resonance condition, the admittance, as we are going for an RLC parallel circuit, we will not discuss about the Z. we will discuss about the admittance. So the admittance of the circuit is in the minimum and equal to the conductance of the circuit. What does it mean? It means we know that the current I, here we are using the Kirchhoff's current law. So I is equal to IR plus IL plus IC. So what is IR? IR is equal to V by R. Sorry, here VS. VS by XL plus VS by XC. So 1 by, and it is V by Z. So 1 by Z is known as the admittance Y is equal to 1 by R is equal to G. 1 by XL is known as the susceptance of the inductor, and 1 by C is known as the capacitance of the susceptance. And if we take the magnitude of this, Y is equal to root of G square plus BL minus BC square. Sorry, BL minus BC whole square. So as we can see that the inductance condition means what is happening, the BL minus BC will cancel out each other and Y will be is equal to G. So we can write is equal to the conductance. Then what will happen? We know that the V by Y is equal, V by Z is equal to current. So we can write here Vy is equal to current. Now if Y is minimum, current should be minimum. This is the main difference of the series resonance and parallel resonance. In the series resonance, current is maximum, but in the parallel resonance, the current is minimum. And again we are getting XL. Actually we have to write that BL is equal to BC. We are writing better. So 1 by XL is equal to 1 by XC. So XL is equal to XC. What is the meaning of XL? 2 pi FL is equal to 1 by 2 pi FC. So F square is equal to, we are getting again 1 by 2 pi root of LC, and omega R is equal to 1 by LC in radian. This both resonance value is same for the both case. So this is the basic series circuit and basic parallel circuit we have discussed. Now we are going for the practical case, or the where the capacitance R and L. In the practical case, R and L is always in series. What is L basically? L is nothing but the inductance. And what is inductance? Inductance means some coil, like choke coil of a tube or any coil is have the inductive property. And when there is an inductance, means one coil, so there should be some resistive property. So L cannot stay alone. L is always connected with the resistance. So in the the coil we are getting R and L always in series, and it may be connected to the parallel of the capacitor. So whenever we are using a pure resistance, maybe the inductance value may be less, but there should be one inductive property. So R and L always in the series combination, and it is the capacitance. So we can see here there is R and C, the current IL is flowing, and this is the IC current is flowing. So what is the current I is equal to, we can write IL plus IC. IL plus IC. So it is the, again we are using the KCL in this point. So if we want to draw the phasor diagram, as this is a what I will tell, this is a series parallel circuit, and both cases the voltage is fixed. So voltage we are taking as the our base equation, or we are taking the voltage as the reference. Now what is happening? This current is flowing through, so this is the voltage across the capacitor, this is the voltage across the resistor. Both is V. Now you can see that the what is the IC current. So as per the civil rule, in capacitor I always leads V. In capacitor I leads V. So IC will be the 90-degree apart from the voltage. So we got the IC. Now we are going for the RL circuit. So here there is a something you have to understand here, what is happening practically in this point. So again, if we draw here, so we are just thinking about this portion. Don't check, we are just thinking about this portion. So here the current IL is flowing throughout the circuit. So we can write IL here. IL is flowing. IL we are taking as the base. So what is VR? This is our VR, the voltage across the resistance, and this is our VL. What is VL? The voltage across the inductance. So what is V? What is V? The V is the, this is the V is equal to VL by VR. Now if we, so what is the angle between this? The angle is phi. So we got the phi angle. Now if we just rotate this is like that. So what is happening here? This is the voltage V. We are rotating this one as the base. So what is IL? IL is in the down. Clear or not? We are just moving the circuits by phi degree. We are moving the circuit by the phi degree. So this is the V and this is the IL and this is the angle phi. So what is the V? V is equal to IL cos phi and it is IL sin phi. So IL sin phi here, you can see IL sin phi or sin IL, this is the phi L, and the IC are always in the phase opposition, and voltage and IL cos phi is in the same direction. So we can write IL sin phi L is equal to IC. Now what is IL? IL is equal to, as this is a series circuit, V by Z, where Z is nothing but the R square plus XL square. From this diagram, we can also tell what is sin phi L. Sin phi L, if this is the phi L angle, what is sin phi L? XL by Z. XL by Z. So we are getting the value. And what is the IC? IC is equal to V by XC. So we got IL, we got sin phi L, we got IC. So what is, we can write here, V by Z is equal to sin phi L, XL by Z is equal to V by XC. We can write like that. Now VV can cancel out. So XL by Z square is equal to XC. We can write XL by Z square is equal to XC. So if we write this XL by Z square is equal to XC, so this is the relation we are getting here. So what is XL? XL is nothing but the 2 pi FL. What is XC? 1 by 2 pi FC is equal to Z square. So 2 pi F will cancel out each other. So we can see omega L by 1 by omega C is equal to Z square. So L by C is equal to Z square. L by C is equal to Z square. And what is Z? Z is nothing but the, what is Z? Z is nothing but the root of L by C. Root of L by C. Then again we can write that Z. What is Z? As we draw this Z, R and L, if you remember the circuit, it is R and L with parallel with C. So Z is equal to R square plus L square. So what is Z square? We got here in the previous one. L by C is equal to Z square. So here we are getting Z square is equal to R square plus XL square. So L by C is equal to R square plus XL square. So what is the thing we are getting here? we are getting L by C is equal to R square plus 2 pi F naught L square. What is F naught? F naught is nothing but the resonant frequency. We are calculating the resonant frequency only. So L by C is equal to 2 pi F naught. So what is 2 pi F naught square? So L by C minus R square. Actually we are getting here 2 pi F naught L square is equal to L by C minus R square. So if I divide it by the L square, what is coming? 1 by LC minus R square by L square. So what is 2 pi F naught? So 2 pi F naught means we are dividing the circuit by L square. So 1 by LC minus R square by L square. So what is F naught? F naught is nothing but the, what is F naught? F naught is nothing but the 2 pi 1 by LC minus R square by L square. If R is very very small, we are getting our basic equation F naught is equal to 1 by 2 pi root of LC. If the multiplication of root of LC is 1 by root of LC is greater than 100 times of the L, we can tell that the R is negligible. So what is, if we put the value, we got the I is equal to V by R, L by CR. This L by CR is known as the dynamic impedance of the parallel circuit of the resonance. So if we put the value, we can get the value of the current also. And current is equal to, if we put the value, we will get VR by L by C. So V by L by CR. So L by CR is known as the dynamic impedance of the parallel circuit. Next, we are going for our important topic of the quality factor. What is the quality factor? The quality factor of an RLC circuit is defined as the ratio of voltage developed across the inductor or capacitor at resonance to the applied voltage which is applied across the resistance R. This RLC circuit can be linked with parallel. So what is quality? The ratio of the voltage developed across the inductor or capacitor at resistor. As we know, the voltage across the inductor and capacitors both are equal, which is the by the voltage across the resistor. So Q factor denotes the energy losses within the resonant devices. What is the use of the Q factor? As we know that the Q factor resonance means the L and C is almost negligible and R is dominant. And R is dominant means there is more loss. L and C is the energy storing passive elements, or R is the energy dissipating passive elements. So what is happening here? The L and C will cancel out each other and R will be used the more energy loss. Q factor denotes the energy losses within our resonant devices. Conditions of high value of Q factor is the value should be high and the value will be R should be lower. Quality. So when we will tell the circuit is more quality, quality factor means R should be lower. R should be lower. As we discussed here, Q is equal to V across L by voltage across resistor, or we can write I by XL by VR means I into R. Now you can see by yourself only that if R is lower, Q will be more. So if we can write, so Q factor is equal to 2 pi into maximum energy stored by energy dissipated per cycle. So maximum energy stored means the voltage across the inductor or capacitor. So Q factor is equal to Q naught is equal to omega naught L by R. Omega naught L by R. So what is that? We can also write 2 pi F naught by R is equals to tan phi also. If we write it by the in terms of C, what will happen? Again 1 by voltage across the capacitor by voltage across the resistor. I into XC by I into R. XC means 1 by omega naught C into R. I cancel out. So omega naught C by R, or we can write 1 by 2 pi F naught R into C. This is also another definition of the Q factor. So, what is the properties of the Q factor? The Q or quality factor of a resonant circuit is a measure of goodness or quality of a resonant circuit. A practical application of the Q is the voltage across the L or C in a series resonant times is the Q times of the total applied voltage. That the voltage across the L or C in the series resonant circuit is Q times of the total applied voltage. Unlike of this, we can tell Q is the current across the L or C in a parallel resonant circuit is Q times of the total current. The frequency response of the circuit current magnitude relates to the sharpness of the resonance in a series resonant circuit. The frequency response of the circuit current magnitude relates to the sharpness. The sharpness of the peak is measured quantitatively and called the quality factor or Q of the circuit. So sharpness, as we have discussed earlier, that if the this is the resonant curve, and if resonant curve means this is the frequency, if this is the current, and we know that the current is equal to, in resonance, V by R. Now if the R value is small, what will happen? It will be some peaky nature. So, and we also know that the Q is also inversely proportional to the R. So for this is called the sharpness. So sharpness and the quality factor is depends on each other. Now we will discuss about the bandwidth. So the response curve for an current versus frequency we are showing here is called the bandwidth. So we know at the resonant frequency the current is maximum. So what is happening? We are what is bandwidth? The bandwidth means when current will reach at the it's 0.707 or Im by root 2 value. We will take this 2 frequency, and this 2 frequency is known as the bandwidth. So the bandwidth of a resonant circuit is defined as the total number of cycles below and above the resonant frequency. Below the resonant frequency and above the resonant frequency. Here you can see frequency value is increasing. So below the resonant frequency and above the resonant frequency. Which current equal to or greater than 70.7 of its resonant value. 70 of 7 means 0.707 into Im is equal to basically Im by root 2. What is this? This is nothing but the RMS value of current. What is this? This is nothing but the RMS value on the current. So why we are getting the RMS value suddenly? The cause is this is a circuit which is basically a resonant circuit, and in the resonant circuit we have discussed that the current is basically, the circuit is basically resistive. So what is the power, or what is the power? Power is equal to I square R. So maximum current we can write Im square into R. Im square into R is the maximum current. So we are calculating it in the half power current. So we can write here I RMS by root 2. I RMS into root 2 square into R. So I RMS square into R by half P. So this point is also known as the half power. So what is written in this section? That the two frequencies in the curve is the 0.707 of the current are called the band. So these 2 points are called the band frequencies. Each is the band frequencies, and the frequencies are identified on the curves as the F1 and F2. We cannot calculate it. We have to plot the scenario and we have to find the F1 and F2, and are often referred as the critical frequencies, cutoff frequencies, and resonant frequencies. Another name is the half power frequencies. So these frequencies are known as the critical frequency, half power frequency, resonant frequency, or cutoff frequency. So in a RLC circuit, the maximum current as resonance is solely determined by the RLC resistive. As I told, in the resonance, the circuit becomes a resistive circuit. But at the off resonance means when there is no resonance, this point, any point when it is an off resonance condition, the current value depends on the Z only. Z means R, L, and C. It depends on the value of R, L, and C. The halfway bandwidth of a circuit is given by the band of frequency which lies between the 2 points of the F0, where current falls about the I0 by root 2. So what is halfway frequency, or what is the bandwidth frequency? The value where the frequencies are false for I0 by root 2. F1 is known as the lower cutoff frequency and F2 is known as the higher cutoff frequency. The narrower the bandwidth, the higher the selectivity. It is correct because if this bandwidth is like this, so the narrower is the bandwidth, the higher is the selectivity. Selectivity means how picky it is in nature, and vice versa. So, as shown in the figure, the half power bandwidth AB, here you can see AB, the half power frequency, we can write delta F is equal to F2 minus F1, or F1 and F2 is the lower cutoff frequency, F1 is the lower cutoff frequency, and F2 is the upper cutoff frequencies. Now, what is the power at the resonance? P max is equal to I max square by R. Now, however, in these 2 points, the current is P1 and P2, and it depends on the half power at resonance. Already I have discussed this in the previous slide, that the power here is equal to half power at the resonance. So that's why it is also known as the half power bandwidth circuit. So the following points are regarding the A and P. This is also known as the half power points, and the corresponding value of the bandwidth is called the half power bandwidth BHP. The following points regarding half power points A and B have some important notes. What are the notes? Current at the half power point is always I max by root 2, or I0 by root 2, or IR by root 2. I max is equal to I naught is equal to IR. All are known as the resonant current, or the maximum current at the time of resonance. What is the value of the impedance? Impedance of these 2 points are also root 2 by R. Root 2 by R. And power is always the half of the maximum resonance power. So, the maximum power we got, the resonance circuit always adjusted to select the band of frequencies. A resonance circuit is always adjusted to select the band of frequencies. We will change the L and C value such that we can get our immediate bandwidth. What is the need of bandwidth? Say you are listening on FM channel. When your channel frequency and your car frequency both are same, you can get the channel. That is called the resonance. We are changing the knob in the car to get one channel. How we are getting the channel? By continuously changing the value of L and C. The smaller the bandwidth, the higher the selectivity. We have discussed many times, the smaller the bandwidth, the higher the selectivity. And now we will discuss the most important topic of this chapter is the relation between the quality factor and bandwidth. As at the resonance, the F1 and F2, we got current is equal to I max by root 2. And what is the impedance we got? We got Z by R. So what is the impedance at the circuit? We know actually Z is equal to square root of R square plus XL minus XC square. These two things we know. Now, at the case of the in the case of the bandwidth, we are getting the half power frequency. What is the meaning of the half power frequency? Half power frequency means I square into Z, or we are getting the I square into Z is equal to actually I, that point I, this is the IRMS, better to write IRMS into root 2 square, I will write like this, Im square Z is equal to, or I square Z is equal to, at that point what is the current? Im by root 2 square into Z. So we are getting the value that the I square Z at the frequency F1 and F2 is equal to Im square by 2 into Z. Now what is the Z actually? Z is the resonance frequency. So what is we are getting here? Z is equal to R. So we are getting, this is also, so 2 I square Z is equal to Im square Z. What is Z? R square plus XL minus XC square into 2 R square. 2 R square at the resonance, Z is equal to R. So we got this. So what we are getting? At the half power frequency, power is equal to I square into Z. And also we can write I square into Z is equal to, what is I max square by root 2 square into Z. We can write. So what is the I square Z here? I am writing here Z dashed. So what is Z? Z is equal to I square Z, and here we can write root 2, so that we can understand this. So we are getting here R square is equal to XL minus XC square. We are getting here R square is equal to XL minus XC square. So there are two conditions in the F1 we know this is a capacitive circuit, so XC is equal, must be greater than XL. So R is equal to XC minus XL. So what is R? R is equal to 1 by omega C minus 1 by omega 1 L. So we are getting one equation, omega 1 square plus R by L omega 1 minus 1 by LC is equal to 0. So what is omega? Omega is equal to R by 2L plus root of R square by 2L square plus 1 by LC. This is the, what is this? This is actually not omega L, this is the omega H, means the lower frequency value. What will happen if XL is greater than XC? Means the second half of a bandwidth. If this is a bandwidth, this is our F1, this is our F2, and this is our resonant frequency. So what is F2? XL is greater than XC. Similarly, we are getting high frequency is equal to R by 2L is equal to R by 2L square plus 1 by L by LC. So what is the omega H and omega L? Omega H means the higher frequency, F2, omega L means the lower frequency. We are getting R plus L. So F2 minus F1, F2 minus F1 is equal to R by 2 pi L. Now again we know what is the quality factor we have discussed, XL naught by R, 2 pi F naught by R. And what is the bandwidth value we got? R by 2 pi L. So 2 pi L by R, or we can write here 1 F naught by R by 2 pi L. So Q is equal to resonant frequency by bandwidth. What is Q? Q is equal to resonant frequency by bandwidth. So, and also we can understand if bandwidth is small, the quality factor will increase. If bandwidth is more, the quality factor will decrease. So these are the relation. We are going for a simple numerical problem. A series resonance network consisting of a resistor 30 ohm, a capacitor of 2 microfarad and an inductor of 20 millihenry connected across a sinusoidal voltage supply which has constant outputs of 9 volt at all frequencies. Calculate the resonant frequency. So what is the formula of resonant frequency? For any circuit, 1 by 2 pi root of LC. L value is given here 20 microfarad, millihenry. L is equal to 20 millihenry and C is equal to 2 microfarad. Microfarad means 10 to the power minus 6. So if we put the value, we are getting the value 796 hertz. Next question is the calculate the current at resonance. Current at resonance means simple V by R. 9 by 30. 9 by 30 means 300 milliampere. The voltage across the inductor and capacitor. We know the voltage across the inductor or capacitor both are same. So we can calculate any one, that is the voltage is equal to 2 pi I into XL. What is that? I into XL. So I into 2 pi FL. So if we put the value, we will get 2 pi FL. F is obviously it is a resonant frequency. See, sometimes we see these mistakes. Many people write at 50 hertz. No, this is the resonant frequency. Remember, the frequency is resonant frequency only. So many people make this mistake. Frequency means is writing the 50 hertz or 60 hertz, but that is completely wrong. So XL is equal to 2 pi FL is equal to 2 pi 796 into 0.02 ohm is equal to 100 ohm. And as VL is equal to VC, so VC value is also so VL value is 30 volt, so VC value will be 30 volt. What is quality factor? XL by R. XL value we have calculated here. R value is given, so Q factor is 3.33. What is the bandwidth? Bandwidth is equal to FR by Q. FR value is given 796 by 3.33 is equal to 238 hertz. So this is the bandwidth value. We are going for another problem. A coil having an inductance of 50 millihenry, resistance 10 ohm and connected with a series of 25 microfarad capacitor. So what is given? It is a practical case problem. So 50 millihenry with a 10 ohm resistance, 50 millihenry with a 10 ohm resistance are connected with a capacitor of 25 microfarad. It is 50 millihenry and it is 10 ohm and everything is connected with a 200 volt AC supply. Calculate the resonance frequency. So what is the formula? We know. So here we can find that the resonance frequency. So actual formula is different, but as we can see, it is 50 into 10 to the 25 million micro. This value, if we take 1 by root of LC, this value is much bigger than the 10 ohm. So we can simply think that the R is negligible. So what is the resonance frequency? The resonant frequency is F naught 1 by 2 pi root of LC and we are getting 142 by 3 hertz. All time check if root of LC is much greater or 100 times greater than R, we can just take the R is the value of R is negligible. What is I naught? I naught is equal to what is the current flowing through the resonance? V by R. V we know 210. So current is 20 ampere. What is Q naught? Q naught is equal to omega naught L by R, or we can write 1 by R root of LC. Any formula you can use for all the cases, the value will come 4.47. Remember that the quality factor is a dimensionless quantity. So for my today's lecture, I have discussed A. Chakraborty's electric circuits book, A. Sudhakar's and Palai circuit and networks books, and the Falkenberg the network analysis book, and the electrotechnology.org website. And this is thank you.
Like, share and subscribe. Hit the bell icon for more updates.